So I'm Rachel Wities from Zebra Medical, and I'm going to talk about hybrid systems and how they can help us break the rule-based barrier in healthcare NLP. So let me start from a somewhat personal note. I was very lucky to do my master's degree in the era of the deep learning revolution. When I started my master's degree, it was, hey, Yoav Goldberg is opening this new seminar in deep learning. Should I go? Is it going to be a thing? And by the time I finished my master's degree, everything was deep learning. You had an NLP problem, you took some sort of LSTM, you took some sort of attention, and this is how you solved it. A year later, I started working in Zebra Medical and got into the healthcare domain. One of the first tasks that I wanted to solve was this task. I had a free text radiology report that a radiology wrote based on an image, and I wanted to translate it into structural labels. Pleural effusion, yes, no, size right, and so on. So coincidentally, the exact months that I joined Zebra Medical, there were two publications solving this exact task. One from QAI in the industry, one of our competitors, and one from a research publication. So this looks really cool and networkish, but these are basically pure rule-based systems. Okay, the left one, QAI, is regular expressions. The right one is rules based on top of dependency parsing tree, which is a little bit more NLP-ish and interesting, but still manually crafted rules. So at this point, I started to feel like I'm living in two parallel universes. I have the universe of academia, where everything is cool and networky and deep, and I have the universe of healthcare, where rule-based systems are still used very extensively. And this is what I want to talk here today, this feeling, the gap that caused this feeling. And I think this conference is an excellent place to talk about it because we have here people both from the research community and from the industry. And I think both those groups can gain a lot from analyzing this gap. So what we're going to do now is, first of all, map the gap. I'm going to show you some nice graphs that show the extent of this problem. Then I'm going to explain why is it like this in industry and specifically in the healthcare domain. And in the end, I want to propose a solution, hybrid algorithms, and give you a few examples of things that were already done in the past few years. So let's start. So I would probably feel a lot better about my parallel universes if I had seen this paper from EMNLP 2013 with the great title, Rule-Based Extraction Information is Dead, Long Live Rule-Based Systems. So here they are mapping the exact phenomenon that I saw. They analyzed 177 NLP papers. They analyzed 41 information extraction systems in the industry, and they found out a huge gap, okay? While in the papers, only 4% were using rule-based systems. And by the way, they add in their paper that when a paper used rule-based systems, it tried to hide it using all kinds of other words instead of saying rule-based. While in the industry, 45% of the systems were rule-based. And the same conclusion was reached by Yoav Goldberg 6 years later in his great talk, The Missing Elements of NLP. Who here have heard this talk? Oh, I expected more. Okay. If you didn't hear this talk, The Missing Elements of NLP, you should hear this talk. It's a very good talk by Yoav Goldberg. So he had there this great slide that says basically what the graphs I showed before told you. Industry uses a lot of regular expressions in 2019. But does this explains the whole gap that I was telling you about before? No, because I didn't just went from the academic world to the industry. I went into the healthcare domain. And in healthcare domain, this gap is even worse. This is a paper that analyzed 263 papers, academic papers, of information extraction in healthcare records, and they show 65% of rule-based system. If we put it next to what we saw before, it's even worse than the industry in general NLP. And if I have to guess how does the healthcare industry looks, this is my guess, not based on anything, I would guess it looks like this, that it has even more rule-based systems. So you can see here the extremity of the gap between the healthcare industry and the NLP research community. Now let's talk a little bit about the reasons to this gap, because there are really good reasons. Basically, it's the same reasons as why industry uses NLP systems, rule-based systems, but on steroids. Everything is worse in healthcare. So small amount of labeled data. Every industry that deals with some kind of specific domain would have this problem. But in healthcare, we have our unique problem of confidentiality. And we need high-level expertise to take the data. We can't just put it on Mechanical Turk and let students from whatever do it. We need at least a medical student and sometimes even a doctor to tag our data. And also, in the medical domain, a lot of the times we have a very low prevalence of the positive cases because some findings are very rare. Another thing that is actually a good thing is that what medical domain has that other domains don't have is rich and very available knowledge bases and knowledge structures. In the graph that I showed you before with the 65% rule-based systems, 54% of them were leveraging some kind of knowledge base. So how does this knowledge base look like? You can see in the picture here, UMLS, a hierarchical structure manually created by doctors, which contains terms for diseases and for location in the body, and a lot of structured knowledge that we would really want to use. And the simplest way to use it, I'll show you later a more complicated way, but the simplest way to leverage such knowledge base is by using rules. Another thing that it's very important to talk about is the human element. We have two human elements in healthcare. First of all, the clinical expert. Whether you're in the industry or in the research, you're working side by side with a clinical expert. And clinical experts don't like to pass their knowledge by annotating thousands of records. They would rather give it to you in the form of rules. Another very important thing is you want to keep the clinical expert in the loop. You don't want him to come to give you all kinds of ideas and rules and then go away while you're training your super cool bird thing and then come back for the evaluation phase. Bad things happen when the clinical expert is left out of the loop. We want to keep them as close as possible, and if we're using something explainable and transferable, then they will stay and transparent, they will stay in the loop more easily. And specifically in the industry, we also have the human element of the doctor, of our clients, and of regulation, which we need in order to be able to work with doctors. A very important thing with doctors is if you want to gain their trust, you need to have transparency and explainability. If they don't understand, they won't trust your system. And the worst thing that can happen to you is non-human-like mistakes. If a doctor sees a mistake that a human could have made, he's okay with it. But if a doctor has a system that has very high precision and recall and everything, but the mistakes he sees are stupid, he won't trust your system. I will give you an example. If someone is trying to label documents for positive or negative for pleural effusion, which is a chest X-ray finding. Okay, so the algorithm can be very good, have high precision and recall, but he might have in his false positive in his false positives, reports that have no mention whatsoever of pleural effusion. How can this happen? Well, one reason it can happen is because pleural effusion highly correlates with other findings, and our algorithm is very smart and understands there's correlation between pleural effusion and other findings. So sometimes, occasionally, he would label a report with other findings that correlate with pleural effusion as positive. Okay, he's actually too smart. But a doctor that sees it will lose his trust immediately. If he would see a dumb mistake that a person could make, if the word was misspelled, if it wasn't in the right place in the report, he would be a lot more forgivable about it. But doctors don't tolerate stupid mistakes. And this is the human element of why healthcare domain uses a lot of rule-based systems. And the last one, well, it works. Okay? It doesn't work as well as neural networks. Every time someone compares rule-based systems with neural networks win. They have higher performance, but it works good enough. You can see here, these are the results of the two algorithms I showed you before, the two rule-based algorithms from QRI and Negbao. The results are quite good. They have above 90% sensitivity, specificity, precision, recall. You can get pretty far only on rule-based systems. And when this is the case, then going and using a deep learning system that will give you 0.5 more precision, but you will lose all the good things we mentioned before, it's just not worth it. So this is basically why we see this huge gap in the healthcare industry. Now let's talk a little bit about the solution. But first of all, I think I was too... I was very, very telling the case of the negative side. So what's the problem? If it works, if it's transparent, let's continue using our rule-based systems and just forget about everything that is being done in NLP. So no, rule-based systems are problematic. They require a lot of human effort. They can't be domain transferred or generalized. If we created a set of rules for pleural effusion and then we go working on intracranial hemorrhage, we'll need to start from scratch, unlike a neural network algorithm that can be retrained with a small set of examples. And another point is that I don't want to lose this connection to the academia. Academia does a lot of great stuff, and I don't want to work separately for them all the time and ignore everything they do. And this is why this gap is a problem. So now let's talk about the solution. So we saw there's a lot of good sides to rule-based. We saw that a lot of good sides to deep learning. Let's try and find a way that we can have both. So in the talk I mentioned before, the missing elements of NLP of Yoav Goldberg, he actually suggests a long-term distance plan of how the NLP research can go from using symbolic systems, rule-based systems, to using deep learning systems together. And he works top-down. He looks, this is where we're now. We want to get there. Let's see what is missing, and let's work in the next few years on these things. I think this is great to have such kind of vision in the research community. I think it's very important, and I'm very curious to see where it's going. But today, I wanted to show you a different approach, a bottom-up approach of algorithms that already exist and keep evolving. And I want to show you a few examples. So the idea of hybrid algorithms is that they contain both rule-based systems and machine learning merged together. I'm going to talk about 3 such algorithms, from the simplest one to a more sophisticated one: Ensemble, knowledge-guided machine learning, and knowledge embeddings. See a lot of cameras, so wait a second. Okay, so let's start from Ensemble. Ensemble is a very simple idea that a lot of machine learning approaches use. We train differently. We train a lot, 2 or more algorithms individually, and then in the end, when we have to take the decision, we see what each of them said and decide based on all of them. So I took here an example of a paper published in 2018, and what they were trying to do is de-identification of healthcare records. Okay, it's a very important task. Before you can do anything with healthcare record, you need to mark and erase all mentions of personal information. So what they did in this study is they trained 12 different algorithms. One of them was rule-based, the PhysioNet D8. Some of them were classic machine learning, and some of them were deep learning. And they created all those different 12 algorithms and created an ensemble between them to get their final decision. And they show something very, very interesting. When you look independently at the independent score of each algorithm, the rule-based system, the PhysioNet died there in the bottom, it performs terribly. You can't use it by yourself. But when they did ablation tests on the ensemble to see how much every algorithm contributes to the whole, it actually contributes quite a lot, more than some of the machine learning algorithms. And I want to add here even more that even if the score was lower, even if in precision and recall it would contribute less, the few mistakes it would fix are those stupid mistakes I talked about that you will be embarrassed by when you show them to the doctor. So even if it doesn't move your precision recall scores at all, it saves you this embarrassment. So it's worth it. Okay, let's move to something a little bit more sophisticated. So here there are a lot of algorithms doing basically the same approach of knowledge-guided machine learning algorithms. They have a pipeline, and in the pipeline they have both rule-based algorithm and deep learning algorithms. I chose here this study from 2019, and they were solving the IB2B obesity challenge. The basic idea is they have discharge summaries of patients in free text, and they're extracting from there 16 labels related to obesity. Obesity, diabetes, asthma, each can be labeled by yes, no, questionable, or unmentioned. So the system that previously was performing based on this challenge was a rule-based system. And probably one of the reasons was that the classes in this dataset are very unbalanced. You can see here that the no and questionable classes have a lot less examples than the yes and unmentioned classes. So what this research with the hybrid algorithms did, they created this pipeline. I will shortly explain it, but I just want to show you that in the end, the green thingy hiding here is a CNN, is a deep learning algorithm. But what happens before it? So 3 interesting things happen before it. First of all, they're using the rule-based system, the SALT system, to mark trigger phrases and label them. And for those classes that have a very small set of examples that can't be trained with an algorithm, they just use the rule-based system as is. Another thing they did is that they didn't train the CNN on all the data, but only on those triggered phrases that the rule-based system said they're important. So what they're doing here is filtering the input to the neural network algorithm with a rule-based system. And the third thing they did, remember that I said before that one of the advantages of healthcare domain is that we have very good knowledge structures that we want to use. So what they did here, they used UMLS, a knowledge structure in the healthcare domain. They extracted from the clinical notes all mentions of terms from this knowledge base, and they also feed them as input to CNN. So their CNN is already getting data filtered by rule-based algorithm and performs better thanks to it. There are 3 things here that they did all together, but I see each one of these approaches is used by itself in many, many papers in the past few years. And the last example I wanted to show you, and the most sort of neural network-ish one, is creating knowledge embeddings. We want to create embeddings that have the knowledge of our knowledge structure. So this, I saw a lot of papers doing it. Some were presented here today in the morning. But what I want, there's still one paper that I still like, most. It's a paper from 2017. And what they did there is that they were trying to leverage DBpedia. DBpedia, I don't know who's here familiar, is a graph, a knowledge graph built on top of Wikipedia. And what it contains is entities connected between them with relations. For example, here you can see that zolpidem is type of drug, and zolpidem is same as Ambien, and zolpidem is exert on kidneys, and so on. Now let's see how do we create those knowledge embeddings. So regular embeddings, we create them while training an algorithm to predict reoccurrences in a corpus. And then what we get is embeddings that are smart as an average person. They have the knowledge of an average person. What they did in this study is they sent this average person to med school. Okay? They trained their algorithm not on predicting word reoccurrences, but on predicting whether a triplet of entity-relation entity exists in DBpedia. And their loss actually takes into account the different types of relations. So what they have in the end is embeddings that are similar to each other in respect to the specific relation they were trying to model in the graph. And when they were using this very smart medical students embeddings together with regular embeddings, they were able to improve algorithms that try to predict healthcare findings in healthcare text. So this, in my view, is a very good example of how we can, in a good way, converge together and infuse knowledge into our neural network systems. So I'll summarize what I said here today. We saw that the healthcare research and industry still use a lot of rule-based system. And we saw that there are good reasons to it that we won't want to just ignore. And we saw a solution or type of solution of hybrid algorithms that might be able to bridge the gap. Now, what we saw here on the degree of integration was from Ensemble, which is the less integrated of all, to knowledge embedding, which already have a sufficient integration between neural network and knowledge base. But what I want to see and what I expect to see and what I'm already starting to see in this industry is even higher degree of integration, where the rule-based system is actually changing the architecture of the neural network, where we can infuse knowledge into the neural network using its architecture and not just by doing some pipeline before. And the one thing I want you to take from this lecture is this. In healthcare, we don't want smarter BERT. We don't want more sophisticated Elmo. We want algorithms that we can plug our knowledge structures and plug our rule-based systems that every healthcare company has, I assure you. And then we can really work with them a lot better. Thank you very much.